Welcome to Lesson 6 of Module 2, where we cover ensembling. Today we will discuss the concept of ensembling, which is combining models to make a better model. We will then go into detail on some ensemble learning methods, including sampling with replacement or bagging, boosting, and stacking. Let's begin with the idea of combining models to make a better model. The goal of ensemble methods is to combine the predictions of several weak models for a single dataset to improve over a single model. Ensembling works by taking a particular ML problem and dataset, choosing an algorithm, for example, a decision tree, and making a model. When the model predictions do not meet the requirements, you decide to build more models by using the same dataset and combining the models to get better predictions. Ensemble learning leverages the idea that many predictions are better than a few, so the ensemble prediction will average out the instability of individual models. Additionally, models that learn differently can help to boost accuracy, even if they are not great individually. The downside is that this takes longer to train, as each model learns separately. As a result, this requires more resources, both in compute and time. The prediction is also more difficult to interpret because it involves aggregating over individual model predictions. Let's dive into some ensemble learning methods. We will start with sampling with replacement, or bagging. Several methods are available to train multiple different models from the same dataset. One method is to first resample the data multiple times by bootstrapping, sample with replacement, from the original dataset. You take sample data points from the full dataset until you have a new dataset of the desired size. Because you are taking samples from the full dataset each time, replacing the sample back into the pool, you will have repeated data points in your new dataset. Usually, about 63% of the original dataset will be in the sample, the remaining data points will be repeated. The result is multiple datasets. Once you have multiple datasets, you train your model on each dataset. Finally, you vote across all models, use statistics to calculate a value, such as the mean, to make a prediction. Important note, why does it need to be with replacement? Sampling data while ensuring the same data distribution within samples is hard to achieve. Certain attributes might be slightly overrepresented or underrepresented. You want to understand the range of possibilities, so you want to build many slightly different models. Sampling with repetition helps you do that. This method also provides variability in samples, even when you take a large sample. 100% sample size is typical. If you tried that with no repetition, you would not have variability. Without repetition, you need to throw out a lot of data to get reasonable diversity in sample datasets. Consider an example with 5 samples instead of 2. This creates a diverse selection of subsets of the data. Sample A, used by model A, sample B used by model B, and so forth. In this simplified example, you take the average of the samples to produce inferences for each model. These models are commonly called weak models or weak learners. They are less likely to have an overfitting problem because they have only samples of the larger dataset to train on. When it is time to make a prediction, you aggregate all the inferences from all the models in some way to produce one final result, which is your final inference. Bagging, which is short for bootstrap aggregating, works by taking a given task or dataset and choosing a simple ML algorithm or weak model. The process starts by bootstrapping multiple datasets from the original dataset. Sampling with replacement is used. This results in independent estimators, which implies that you could easily parallelize bagging for speed and functionality. You can bag any estimators, but the most popular bagging model is bagging trees, known as random forest. Bagging is useful when you have estimators that have a variance problem. You can identify this when your training errors are much lower than the validation or test error. Bagging reduces the variance, does not increase bias, and therefore causes the test error to go down. It uses majority vote or average the predictions from all estimators. Scikit-learn has a general interface for bagging. You can provide any base underscore estimator, a classifier or a regressor. When bootstrap equals true and random subsets of the dataset are drawn with replacement, bagging is being implemented. The number of samples to draw from X to train each base estimator, max underscore samples, default equals 1.0, and with replacement is the default. For more information, see the scikit-learn bootstrapping documentation. Random forest is an example of bagging by using a combination of multiple trees. It implements the bagging algorithm. Step 1, draw random subsets with replacement from the original dataset, generating n datasets, data 1, data 2, and so on. Step 2, build a decision tree on each bootstrap subset. Step 3, combine metrics from each tree for final prediction. How does random forest help improve performance? Random forest is a combination of decision trees. Decision trees typically have low bias because they are usually allowed to grow in depth until the training error is sufficiently low. The challenge with decision trees is high variance, which leads to overfitting tendencies. Bagging helps reduce variance by combining multiple trees that are trained on bootstrap datasets. Bootstrapping helps create an ensemble of usefully varied decision trees. Combining the predictions of the decision trees reduces the variance of the overall predictor. This helps random forest to overcome the high variance problem that comes from using bagging with decision trees. Scikit-learn's ensemble module has random forest classifier and regressor functions. There are a mix of bagging-specific and tree-specific parameters. Bagging-specific parameters, n_estimators, default 100, defines the number of trees to be modeled. Max_samples, default none, defines the number of samples to draw from the original data to train each tree, the size of the bootstrapped subsets. Tree-specific parameters, criterion, Ginny here, defines how to decide the splits, entropy, as well. Max_depth, default none, defines the maximum depth of a tree. Used to control overfitting because higher depth will allow the model to learn relations that are specific to a particular sample. Min_samples_split, 2 here, defines the minimum number of samples or observations that are required in a node to be considered for splitting. Used to control overfitting because higher values prevent a model from learning relations that might be highly specific to the particular sample that is selected for a tree. Values that are too high can lead to underfitting. Therefore, it should be tuned using cross-validation. Min_samples_leaf, 1 here, defines the minimum samples or observations that are required in a terminal node or leaf. Used to control overfitting, similar to min_samples_split. Generally, choose lower values for imbalanced class problems because the regions in which the minority class will be a majority will be small. Class_weight, default none, defines weights associated with classes in the form. Class_label, weight. The balanced mode uses the values of y to automatically adjust weights inversely proportional to class frequencies in the input data. Now let's discuss a second method, boosting. Ensemble methods try to train multiple weak models to improve the prediction on a given task. However, these weak models need to be different because if the dataset is the same and the model is the same, all the models will make the same predictions. This is not very useful and doesn't serve the goal. How and what can you change to train and get different, still weak, models while using the same source dataset and same algorithm, while improving the prediction for the task? You want something better than bagging. Bagging is trained on different subsets of the original dataset, but it basically averages the predictions of weak learners with the same frozen hyperparameters. What if you modify the weak learners to become better, so the ensemble becomes better at making predictions that are closer to the true target values? Boosting is an ensemble method that creates a strong model by combining the predictions of multiple weak models that are built with a given dataset and a given learning algorithm. Specifically, boosting builds multiple weak models sequentially. Each subsequent model attempts to boost performance overall by reducing the errors of the previous model. Consider an example where the first weak learner, weak model 1, trains on the given dataset, data 1, with features X and target Y. Next, weak model 1 is used to make prediction Y hat1, which is far from target Y. The large difference between Y and Y hat1 indicates a large error, which will need to be addressed. For this ensemble, you need to keep track of the ensemble prediction, for now, Y hat1, because that's what weak model 1 gave. The plan is to build the next model in the ensemble such that the prediction of the ensemble is closer to the target Y. The plan is to slightly adjust the dataset and algorithm to focus on the large error. The general idea is to work to minimize the error, so the ensemble becomes a better learner overall. The key idea of boosting is to have the next model focus on this error, the residual of the previous model. The residuals are the data samples that the previous model found difficult to predict. To do this, weak model 2 focuses so much on weak model 1's error that this error becomes its target. Keep in mind that, while the algorithm in principle stays the same, if weak model 1 was a tree, weak model 2 will still be a tree. Weak model 2's hyperparameters are adjusted as informed by the error. Essentially, both the initial training dataset and the initial weak model are adjusted according to the previous error to build this new model. The new model is added to the ensemble with the goal of improving the ensemble's prediction and minimize the overall errors. Weak model 2 trains on data 2, which has the same features, x, but a new target, y minus y hat 1. Weak model 2 makes prediction, y hat 2. Overall, the ensemble got a bit bigger, so you need to keep track of the ensemble prediction, which is now y hat 1 plus y hat 2. With a focus on the initial target y, if there's still a large error between the target y and the ensemble prediction y hat 1 plus y hat 2, meaning y minus y hat 1 minus y hat 2, you need to continue to build more weak models for other hard-to-predict residuals, adding more weak models to the ensemble. Again, make adjustments to predict better on this error, focusing on this last error, to the extent of making it closer to the target y. By adding each new weak model to the ensemble sequentially, you are trying to overcome or reduce the errors of the previous model. You might notice that the boosting method sounds a bit like gradient descent. The boosting ensemble is typically constructed from decision tree models. Trees are added one at a time to the ensemble and fit to correct the prediction errors that prior trees made. Subsequent trees are fit using a differentiable, loss function, and gradient descent optimization algorithm. The technique is known as gradient boosting machine, GBM. Because decision trees are typically used as the weak learners in GBM, this technique is also known as gradient tree boosting or gradient boosting. Gradient boosting is an effective ML algorithm and is often the main, or one of the main, algorithm that is used to win ML competitions, such as Kaggle, on tabular data and similarly structured datasets. The most used boosting implementation comes from scikit-learn. Additional third-party libraries provide computationally efficient alternate GBM implementations that often achieve better results in practice. The following are a few examples. XGBoost, Extreme Gradient Boosting. XGBoost is engineered for efficiency of compute time and memory resources. XGBoost is free open-source software that you can import in your Jupyter Notebooks. LightGBM, Light Gradient Boosted Machine. LightGBM is a library developed at Microsoft that provides an efficient, fast implementation of the gradient boosting algorithm. You can also install the LightGBM library in Python. The LightGBM library also provides wrapper classes so that you can use the efficient algorithm implementation with the scikit-learn library, specifically through the GBM classifier and the GBM regressor classes. CatBoost, Category Gradient Boosting. CatBoost has the primary benefit of support for categorical input variables, along with computational speed improvements. You can install the CatBoost library in Python. The library provides wrapper classes so that you can use the efficient algorithm implementation with the scikit-learn library, specifically through the CatBoost classifier and CatBoost regressor classes. In scikit-learn, the ensemble modules provides a boosting classifier and a boosting regressor. The gradient boosting classifier can be used with fit and predict. The full interface is larger, and notice the mix of boosting-specific and tree-specific parameters. Finally, our last ensemble learning method is stacking. Stacking is a way to ensemble multiple classification or regression models. The idea is to solve the prediction problem with different types of models that can learn some part of the problem, but not the whole space of the problem. You can build multiple different predictors, build an intermediate list of predictions, and use a meta-learner to learn from these predictions to predict the final outcome. Stacking often results in a prediction score that is better than any of the individual models. With bagging, multiple similar models with high variance are averaged to decrease variance. With boosting, multiple incremental models are built to decrease the bias, while keeping variance small. Stacking is a different paradigm. It explores multiple models for the same problem and combines their individual predictions to build a stacked model that can make a better prediction. Stacking allows all models to be different, unlike bagging, and models in a layer can be trained in parallel, unlike boosting. AutoGluon can make high-quality predictions by using a multi-layer stacking solution. You can extend stacking to more than one layer by using the stacker models as base models for other stacker models. Note that the input features are also concatenated along with the base model's predictions to enrich the data that is used to train the stacker models in the next layer. To make the most of stacking, it is good practice to use a diverse set of models where each is capable of handling the problem in a different way. Combining the predictions of these models significantly improves performance. Ensemble methods are techniques that combine multiple models to improve predictive performance. Bagging involves creating independent estimators and averaging their predictions. This approach helps reduce the variance of individual models, making it useful when models suffer from high variance. Boosting builds models sequentially, with each new model attempting to correct the errors of the previous combined estimator. This process aims to reduce bias, making boosting effective for models with high bias. Stacking is a more flexible ensemble method that trains different independent estimators and uses a meta-learner to combine their predictions. This approach can leverage the strengths of different model types and often leads to improved performance. Multi-layer stacking can improve performance, but be careful of overfitting. In this lesson, you learned how to combine ML models to make more powerful predictions. Combined with the previous lectures, you now understand many of the core technologies that make up AutoGluon. Next, you will learn about responsible AI/ML practices to ensure that you approach ML problems responsibly. Thank you for your attention.